Now with that set of problems on the second unit, we'll go to the third unit on recurrence relations. We discussed a lot of topics under recurrence relations. We talked about how to evaluate a polynomial telescopically. We talked about classifying a recurrence relation into homogeneous, non-homogeneous types, and we gave a specific definition for the order of a recurrence relation. We understood what a characteristic equation is and how to find out the general solution of the particular solution of a given relation, and we also saw how to solve a recurrence relation using a generating function. We'll have a look at a set of questions on this unit in the MCQ types. We have a sequence here. The sequence is 1, 7, 31, 127 and 511. We're trying to find out the corresponding recurrence relation here. The first term is 1, so all of them have b naught to be 1. That's all right. Which of these options is right? Now let's have 1, 7, 31. Now there is no hard and fast rule to guess the recurrence relation here. It only works on a trial and error basis. So what happens here is 1 goes to 7, which is 1 times 7, or 1 times 6 plus 1, 1 times 5 plus 2, 1 times 4 plus 3, etc. And 7 goes to 31. The connection between 7 and 31 is 7 times 5 minus 4, or 7 times 4 plus 3. That might work. 31 goes to 127, and 127 is 31 times 4, which is 124 plus 3. So you will see that there is a pattern here. 7 is 1 into 4 plus 3, 13 is 7 into 4 plus 3, and 127 is 31 into 4 plus 3. The next number, 127 into 4 plus 3, is what should be the next number. 127 times 4 is 508, plus 3 is 511. That matches, and you will have this as your answer. So there is no hard and fast rule to guess the recurrence relation. Now if you have a recurrence relation, you can solve it and get the terms of the sequence. But if I don't give you the recurrence, I give you only the sequence, then it takes some common sense and intuition to solve it. We have done it here. Okay, now this is based on terms of the sequence. A sequence is being defined using the recurrence relation. An is an minus 1 times 2 plus 3. And you have the base condition a naught as 6. Now we are asked to find out a4. Now a4 clearly is 2 times a3 plus 3. But you don't have a3. So what is a3? a3 is 2 times a2 plus 3. You don't have a2 also. a2 is 2 times a1 plus 3. You don't have that. But a1 is 2 times a naught plus 3. You know this. A naught is 6, so 2 times 6 is 12, 12 plus 3 is 15. And 2 times 15 is 30, 30 plus 3 is 33. And a3 is 2 times 33, which is 66, plus 3, which is 69. And a4 is 2 times 69, which is 138, plus 3, which is 141. That matches with the option C. That's how you understand a recurrence relation. You build it, you break it down till you reach the initial condition, and you build it up from there. Similar exercise again. This time we'll have to find out the fourth term of a sequence. You have a naught is 2. So a naught is 2. Let's find out a4. A naught. So a4 is a3 plus 2 into 4. And a3 is a2 plus 2 into 3. a2 is a1 plus 2 into 2. And a1 is a naught plus 2 into 1. You know what a naught is? A naught is 2. So that's 2 plus 2, which is 4. 4 plus 4, which is 8. 8 plus 6, which is 14. And 14 plus 8, which is 22. So he asks you for the fourth term. So a naught, a1, a2, a3, a4 is the sequence that you have. So a naught is 2, a1 is 4, a2 is 8, a3 is 14, a4 is 22. The fourth term of the sequence is 14, and that qualifies as the right answer. Okay. Next up, we are trying to solve a recurrence relation this time, and we'll try and do it. Now if you can recall, this recurrence relation has an order of 2, because you have bn minus 8 bn minus 1 plus 12bn minus 2 to be 0. So it is clearly a recurrence relation of order 2 because the last subscript ends with 2. And how do you solve such answers? You find the characteristic equation. The equation is r square minus 8r plus 12. You can solve this and get the answer for r is 6 or 2. So you will have the general solution of the form b1 times 6 power n plus b2 times 2 power n. Clearly that is obtained only in the first step. The others are different, but anyway, let's solve for b1 and b2 again and check if the answers are right. You are told that b0 is 3, so b1 plus b2 is 3, and 6b1 plus 2b2 is 4. So I'll multiply the first one by 2 and then subtract. So this is 4b1. When I subtract, this becomes 0. This is 2. So b1 is minus half. If b1 is minus half, b2 is 3 plus half. 3 plus half is 6 plus 1, 7 by 2, that's 3.5. So one is 3.5 and the other is minus 0.5. That happens to be the first option, and that's right. And determine the value of a2 for the recurrence relation. Once again, this is a linear first order recurrence relation which is non-homogeneous. So a0 is 3 and we're asked to find out a2. a2 is 17a1 plus 30 into 2. You don't know a1, so a1 is 17 a0 plus 30 into 1. a0 is 3, so this is 17 times 3, which is 51 plus 30 is 81, and this is 17 times 81 plus 60. 17 times 81, 80 is in fact 17 times 81, right? 17 eighths give you 136. 136 or 1360 is what we have here. 1360 plus another 17, so that's 1377. This is 7. Okay. 17 times 80. So 17 times 81 is 1377. And when you add 60 to it, you will get 1437, and that's what you have. The last option is your A2. Now we are back to the guessing game. We are trying to find the recurrence relation for the sequence 1, 4, 13, 40 and 121. We'll have to do a trial and error basis here. So 4 is 1 times 1, 1 times 4, okay, or 1 times 3 plus 1, or 1 times 2 plus 2, etc., so on and so forth. And 13 is 4 times 3 plus 1, 4 times 2 plus 5, 4 times 1 plus 9, etc. 40 is 13 times 3 plus 1, 13 times 2 plus 14, 13 times 1 plus 27, etc. So the pattern that you find here is 1 times 3 plus 1, 4 times 3 plus 1, 13 times 3 plus 1. So if you look at option B, it's option C says Bn is 3 times Bn minus 1 plus 1. That's in fact right. These two are in the subscript. This is 3Bn minus 1 plus 1. This is Bn minus 1 plus 1. And this fits the answer best. Final answer. Okay. Next we are trying to find a simple form of the given sequence 1, 4, 10 and 28. We'll have to guess the answers again. Okay, this time we'll do it the other way because 1 goes to 4 and there are a couple of subtractions also involved. So 4 is 3 times 2 minus 2, 10 is 3 times 4 minus 2, 28 is 3 times 10 minus 2. So you will see that it is 3 times Bn minus 2, which fits the bill. And again a recurrence relation for 1, 5, 21, 85, 341, etc. 5 is 4 plus 1, 21 is 4 times 5 plus 1, 85 is 4 times 21 plus 1, 84 plus 1, and 341 is 4 times 85 plus 1. That corresponds to option C. That is once again right. And this other recurrence relation, once again this time we are doing as 8 times. Okay, 8 is 1 times 7 plus 1, 43 is 1 times 42 plus 1, there is no connection. Or you can also write this as 1 times 5 plus 3, this is 8 times 5 plus 3, 218 is 43 times 5 plus 3, 43 and 5 give you 2 and 5 plus 3 is 218, and 1093 is 218 times 5 plus 3. 218 times 5 will be 1090, 3 added to that is 1093. So option A is in fact right. Okay, now this is also what we discussed some time back, how to reduce a polynomial telescopically. We have a quintic polynomial, a polynomial of order 5. We are trying to reduce it telescopically. You have 30 y power 5 minus 16 y power 4 minus 5 y cube plus 23 y square, etc. So when you reduce this telescopically, you will have to first separate this 30 y minus 16 is what you will have to start with. You will gradually increase the power, so you will have a y, and the next term is minus 5 y cube, so there is a minus 5, a y again, and a 23 y square, there is a plus 23, and another y in the front, and the last term is a 12 y, so it's a 12 and a y again, and to that you subtract y. So 30 into y, 30 y square, 30 y cube, 30 y power 4, 30 y power 5, that term is right. Minus 16y, minus 16y square, minus 16y cube, minus 16y power 4, that is again right. Minus 5y, minus 5y square, minus 5y cube, that's also matching. 23y, 23y square matching again. 12y comes only once, 8 appears once. So which of these 4 options suit this given expression best? You will see that it is option C. Option C is the actually correct form of the telescopically reduced polynomial. Next one is again a polynomial of order 6 this time. It's not a 5, this is 6. 3y power 6 minus y power 5 plus 24y cube. That's the problem. You don't have a y power 4. A y power 4 is missing. You will account for that. So you will just have to write 0 y power 4. So when you do this, you will start the 3y minus 1. You will include a y, that's all right, because you need the y power 5, but you don't need the y power 4, so that's a 0 and a y outside, plus 24 with another y outside, minus 96 and another y outside, plus 9 and another y outside. There is no constant to add, there is nothing to add on the right. Let's check this: 3y square, 3y cube, 3y power 4, y power 5, y power 6. That matches. Minus y square, minus y cube, minus y power 4, minus y power 5. That matches. 0y square, 0y cube, 0y power 4, 0y power 4. 24y square, 24y cube, that matches. 96y square also matches. 9y also matches. So this is the final correct expression, and this matches with yes, there are 2 options which may seem correct, but not all of them are right. Okay. This is 0y, so this doesn't matter, so it is a y times y, that's right. Option, the first option is what suits best. Here in the second option you have a y directly, and this y power 4 is missed, so you will have only a 24y square, you will have 1 power less everywhere. You will have a option B talks about y square, y cube, y power 4, y power 5, 3 y power 5. You don't have y power 5 here in front of the number 3, so option B is wrong. Option C talks about a y and a y again, but it talks about a minus 24. Minus 24 is not what we have, and option D is the same as option B, except that the signs are flipped, so even that can't be right. So only option A suits the answer best. Now with that problem we have completed the set of questions which are on the revision for these 3 first units. For units 4 and 5 we have already discussed problems during the lectures itself, so that should give you enough revision on the first 3 units. We'll stop right here. Thanks. Okay, next up we'll have a revision problem on how to solve a recurrence relation using the concept of generating functions. Now on your screen you can see a second order linear recurrence relation which is homogeneous. How do we know it is second order? We have n minus 2 as the last index, and we have 2 extra information which are given as part of the problem. Therefore this recurrence relation is of second order and there is no function of n on the RHS, which means the recurrence relation is also homogeneous. Now we have already solved a lot of problems of this kind using the simple algorithm that we discussed. Now to do a final revision on recurrence relations, let's try and solve this using generating functions. Now if you can recall, the generating function that we used is defined in this form, where every term is made of 2 components, a constant namely ai, aj, ak, etc., and a power of x as in x power i, x power j, x power k, etc. The summation runs from 0 to infinity, and this is what we call as the generating function used to solve any given recurrence relation. Now in that aspect we will try and solve this RR using this technique of generating functions. Now let us rewrite the given equation so that it is convenient to us to solve this problem using the idea of recurrence relations. So this is what we have, where an denotes the nth term of the sequence, an minus 1 represents the n minus first term, and an minus 2 represents an minus second term. So this is what we have. To solve this using recurrence, to solve this using generating functions, we will multiply throughout by x power n and do a uniform summation. So let us first multiply this, an x raised to n minus 7 an minus 1 x raised to n plus 10 an minus 2 x raised to n, all of them giving 0. Next up we will do a uniform summation, so it will be summation an x raised to n minus 7 times summation an minus 1 x raised to n plus 10 times summation an minus 2 x raised to n. Now since this summation has to be uniform, let us sum them up from a common starting point which is 2. We have already discussed why it cannot be 0 or 1, because the other 2 summations will have no significance if we begin from 0 or 1. If we begin from 0, this summation will start from a minus 1. That does not make sense when you start to refer terms of the sequence with the index as n. If we start from 1, this will also begin from a minus 1, that won't make sense. So the common starting point has been a naught or a subscript 0. Now to have that kind of a subscript, we begin at 2. All of the summations are uniformly started from 2. So this is a2, this is a1, this is a0. That makes sense. Alright, now the second thing that we discussed is to introduce this g of x into each of these summations. To do that we did a small adjustment that depended on what we understood as this summation. This summation actually is a0 x power 0 plus a1 x power 1 plus a2 x square, so on and so forth. Now the common thing about this generating function is the index of the subscript and the index of the exponent are one and the same. So to introduce g of x into this equation named as 1, we will have to have a common index at the subscript as well as at the exponent. Now we will deal with each of these summations individually and ensure that they start at the right point. Now the first summation we have is from n is equal to 2 to infinity an and x power n. Now this is actually from a2 x squared, a3 x cube, so on and so forth. Now you can see that what are missing from here is, this is missing the first two terms, the a naught x power 0 plus a1 x power 1 plus whatever we had already. These two terms are what is missing. So g of x is actually this part. Now when you compare both, when you compare what we have in the summation and what we have in the definition of g of x, it is obvious that we are missing the first two terms. So to make the adjustment regarding that, we will write this equation as g of x minus the first term a naught x power 0, the second term a1 x power 1. So that is what we have. The very first summation involved in solving the recurrence relation using generating functions is written in this form. It is similar to g of x, except it is missing two terms, or it is nothing but g of x minus a naught. A naught is the value of the sequence at 0, which is 4 x power 0 minus a1 is 17 x power 1. So what we have is g of x minus 4 minus 17x. That is what we have. Now the second summation that we had was once again from the same term 2 up to infinity. It began with a n minus 1 x power n. Now the indices at the subscript and the exponent are not identical. So to take care of that, we will factor out 1x outside and write this as 2 to infinity a n minus 1 x n minus 1. Now this is nothing but x times, when n is 2, n minus 1 is 1, a1 2 minus 1 is 1. Now the indices are identical, a2 x squared, a3 x cube, so on and so forth. So that is what we have as the summation. Now when you compare this with g of x, this is g of x minus, or g of x from which we have removed only the first term a naught x power 0. So what we have is simply x times g of x minus a naught is 4, so that is just 4. Or in other words, the second summation, which is part of the recurrence relation a n minus 1 x raised to n, is x times g of x minus 4x. The last part, and you had a 7 in the front, so this is all multiplied by 7. So you have 7x g of x minus 7 times 4, that is a 28 and an x. Now to sum it up, we will look at the last summation here. The last summation started from 2 to infinity and it went on from a n minus 2 x power n. So the summation must go as x square times 2 to infinity a n minus 2 x power n minus 2. Only then the indices will be identical. So this gets simplified as, or in other words, you will have 2 minus 2 is 0, 2 minus 2 is 0. So you will start with a naught x power 0, a1 x power 1, a2 x squared, so on and so forth. This is exactly identical to what we saw in the definition of g of x. So the last term of the summation is just going to be x squared times g of x, and since we had a 10 in the front, the last summation was 10 times 2 to infinity a n minus 2 x n. So that becomes 10 x squared times g of x. So we have one answer each for each of the summations and we can write them down. So one was 7x times g of x and 28x together, and the other was 10x squared g of x. The previous slide we saw that we had g of x minus 4 minus 17x. So using them all in this final equation, we have our answer. We have one answer for this, one for this, and one for this. This was just 10x squared g of x. This was minus 7. This was minus 7x g of x plus 28x. The last term, the first term was g of x minus 4 minus 17x. So each of the summations has been represented in the form of the generating function, which means we are free to start solving and identifying what the generating function is. That is what we will do in the next slide. So we have g of x minus 4 minus 17x minus 7x g of x plus 28x plus 10x squared g of x, all of them giving us 0 as the RHS. So grouping the like terms, we have g of x times 1 minus 7x plus 10x squared minus 4 plus 11x giving us 0, or you can rewrite this as g of x times 4 minus g of x is 4 minus 11x upon 1 minus 7x plus 10x squared. To solve the remaining part, we will have to resolve the denominator into two first order linear factors, and that is pretty easy because you will have 4 minus 11x upon 1 minus 2x and 1 minus 5x. That is how you can factorize the quadratic expression here. So when you rewrite it as a upon 1 minus 2x and b upon 1 minus 5x, we can start solving for a and b. So you will have to compare 4 minus 11x with the LCM of these two fractions, a times 1 minus 5x plus b times 1 minus 2x, and that will give us the required answer. If x is half, we have 4 minus 11 upon 2 giving us a times 1 minus 5 by 2 plus 0. 1 minus 5 by 2 is minus 3 by 2a. 4 minus 11 by 2 is 8 minus 11 by 2 minus 3 by 2. So minus 3 by 2 is minus 3 by 2a, or a is 1. Similarly, if x is 5 by 2, x is 1 by 5, we have 4 minus 11 by 5 giving us a times 0 plus b times 1 minus 2 by 5, which is 20 minus 11, 9 by 5 giving us b times 5 minus 2 by 5, which is 3 by 5, or b is 3. So a is 1 and b is 3, which means we have the partial fractions as 1 minus 2x plus 3 upon 1 minus 5x, and that is enough for us to write the answer in terms of the power series or the generating function. So our g of x will be of this form: 1 times, you can recall that 1 upon 1 minus 2x is 1 plus 2x plus 2x the whole square plus etc. The next one was 3, the next constant was 3, so 3 times 1 plus 5x plus 5x the whole square etc. So when you write down and add the like terms together, you will have 1 plus 3 as the first term, 2 plus 3 into 5 times x as the second term, 4 plus 3 into 5 squared times x squared as the third term. So when you look at the coefficients specifically, you will have 1 power 0 plus 3 power 0, 2 power 1 plus 3 times 5 power 1 plus 2 power 2 plus 3 times 5 power 2 times x squared etc. So when you write them down as exponents of n, you will have 1 times 2 power n plus 3 times, this is 5, yeah, this is 3 plus 3 times 5 power n common and multiplied with x power n. So your a n is simply 1 times 2 power n plus 3 times 5 power n, or in fact the nth term of the sequence can just be obtained as s of n is 1 times 2 power n plus 3 times 5 power n, and that solves the given recurrence relation. You can always verify this from the question. S of 2 is going to be 7 times s of 1 minus 10 times s of 0. S of 1 is 17, which is 7 times 17 minus 10 times 4, that's 119 minus 40, which is 79. The same 79 will be obtained when you substitute 2 for n, that's 1 times 2 squared plus 3 times 5 squared, which is 4 plus 25 times 3, which is 75, and that is again 79. So this is the evidence that we have solved the given recurrence relation correctly using the idea of generating functions. We will just solve one more problem and then wrap up this unit on recurrence relations. This time we have a non-homogeneous recurrence relation, just easily identifiable from the 2 on the RHS. It is not a 0, it is a constant function that we have. So we will have to solve this once again using the principle of generating functions. So if you can directly go into what are required here, we will write them down as a n minus 5 a n minus 1 plus 6 a n minus 2 giving us 2. So when you do the summation, the common summation from 2, you will have a n x n 5 n of n is equal to 2 to infinity a n minus 1 x n plus 6 2 to infinity again a n minus 1 x a n minus 2 x n. The last one is 2 times 2 to infinity x power n, there is no a n here, only x. So like we saw in the previous problem, we can simplify each of these summations in terms of our generating function g of x, which is n is equal to 0 to infinity a n x power n. The first summation, since it starts from a n a2 x power 2, we will have to remove the first 2 terms. So the first one is a naught minus a1 x, this is your first summation. I will substitute the values shortly. The next one is minus 5 times, this time we will have to remove only the first term after factoring out the x outside, that is going to be g of x minus a naught. The last one we do not have to do any adjustment except for factoring x square out, so 6 times x square times simply g of x, because once you adjust the indices you will see that it exactly starts with a naught x power 0, a1 x power 1 plus a2 x squared, so on and so forth. Next up we can try and substitute, and on the RHS we do not have any g of x, we simply have 2 times n is equal to 2 to x power n. We will simplify that shortly. So a naught is the first term of the sequence given to be 2, so that is 2 minus 5x minus 5x times g of x minus 2 plus 6x squared g of x, giving us 2 times the summation here is x squared plus x cube, etc. We will have to think about that, we will do it on the next slide. So the like terms can be grouped, we will group that next. So we have g of x times 1 minus 5x plus 6x squared, the constants will be minus 2 minus 5x plus 10x. So we will have minus 2 minus 5x plus 10x. Now the RHS we have 2 times x squared plus x cube, so on and so forth. What we do not have is 1 and x. If we have 1 and x, we can write it as 1 upon 1 minus x. So recall that 1 upon 1 minus x was 1 plus x squared, etc. Since we don't have these, we can subtract them from this summation and write the expression on the RHS pretty easily. So that's 2 times 1 upon 1 minus x, from which we have already removed the first 2 terms. Simplifying the rest, we have g of x times 1 minus 5x plus 6x squared minus 2, 10 and 5 give you 5 again, plus 2 times 1 upon 2 upon 1 minus x minus 1 minus 2 minus 2x. We can lose these 2 terms and rewrite the remaining. So we have g of x times 1 minus 5x plus 6x squared, and on the right we have minus 2 minus 2x minus 5x, which is minus 7x. Simplifying, we have 2 minus 7x plus 7x squared upon 1 minus x. So g of x happens to be 7x squared minus 7x plus 2 upon 1 minus x times 1 minus 5x plus 6x squared, which means you have 3 factors, 3 linear factors at the denominator, which are 1 minus x, and these 2 can be simplified as 1 minus 2x and 1 minus 3x. So to identify the generating function, we will have to resolve this rational function into partial fractions, and that is what we will do. The next slide. So we have g of x to be seven x squared minus 7x plus 2 upon 1 minus x times 1 minus 2x times 1 minus 3x, which is also a upon 1 minus x plus b upon 1 minus 2x plus c upon 1 minus 3x. And now we will have the numerators being compared after determining the LCM, which means a times these 2 plus b times the first and the last and c times the first 2 terms. So to solve for a, b and c, let us first substitute x as 1. If x is 1, it is 7 minus 7 plus 2, and a times 1 minus 2, which is minus 1, 1 minus 3, which is minus 2, b times 0, c times 0. Therefore 2 is minus 1 times minus 2 times a, or 2a is 2, which means a is 1. That is the first we have. And next, if we plug in x is half, we will have 7 upon 4 minus 7 upon 2 plus 2 equaling a times 0 and c times 0 and b times 1 minus half and 1 minus 3 by 2. So we have 2 equaling b times, or this LCM makes it 7 minus 14 plus 4 into 2 upon 4, which is minus half plus half and minus half. Or you have 8 plus 7, 15 minus 14, which is 1 by 4. 1 by 4 is b times minus 1 by 4, or b is minus 1. We have only one last constant to find out, and for that let us use x is 1 by 3. Then we will have 7 upon 9 minus 7 upon 3 plus 2 equaling a gives us 0, b gives us 0, and c times we have 1 minus 1 by 3 and 1 minus 2 by 3. 1 minus 1 by 3 and 1 minus 2 by 3. Therefore we will have 7 minus 7 times 3 plus 2 times 9 upon 9 equaling A and B are gone. 1 minus 1 by 3 is 2 by 3 into C minus 1 by 3 times C. So we have 18 plus 7 is 25 minus 21 is 4 by 9, giving us 3 minus 1 is 2, 3 minus 2 is 1. That's what we had. Yes. So this is even plus 3 times 3 minus 2 is 1 by 3. So that's 2 by 9 into C, or C gives us the answer as 2. So simplifying, we have A as 1. So g of x is given by 1 upon 1 minus x plus B is minus 1 minus 1 upon 1 minus 2x plus C is 2. C is 2, which means we will have 2 upon 1 minus 3x. So writing them down as generating functions, we will have the first summation as 1 plus x squared, etc. The second summation as 1 plus 2x plus square of 2x, etc. The last summation as 2 times 1 plus 3x plus square of 3x, etc. Therefore the generating function, which is going to return all the coefficients, can be obtained by grouping the constants first and the x terms first, the x squared terms next. So we will have 1 minus 1 plus 2 as the first term plus x is 1 again, 1 minus 2 plus 2 times 3, which is this coefficient of x. Next term is 1 minus 4 times 1 minus 4 plus 2 times 9 upon x square, etc. So therefore the coefficient can be easily written as, we will have a 1 everywhere plus a 2 times a power of 3, which is next. This is 2 times 3 power 0 minus 2 power 0, that is what we have. This is the very first term. The second term is 1 plus 2 times 3 power 1 minus 2 power 1. The second term is 1 plus 2 times 3 squared minus 2 squared times x squared, etc. So in general the coefficient can be written as 1 plus 2 times 3 power n minus 2 power n, and that the general term a n x power n is all of this multiplied by x power n, and that gives us the solution of the recurrence relation. It is in fact 1 plus 2 times 3 power n minus 2 power n. If you wish, we can even verify this answer from the question. We know that s of 2 is 5 s of 1 minus 6 s of 0 plus 2. S of 1 is 5, so it is 5 times 5 minus 6 times s of 0. S of 0 is 2, that is 6 times 2 plus 2, which is 25 plus 2 minus 12, which is 27 minus 12, which is 15, and the same 15 will be obtained from here. From here s of 2 is 1 plus 2 times 3 squared minus 2 squared, which is 1 plus 2 times 9 is 18 minus 4, 19 minus 4 is still 15. So the same 15 has been obtained by two different methods, which means we have solved this recurrence relation perfectly using the technique of generating functions.